Welcome to 5.5 double angle identities. We will look at example 3 today where we need to verify the identity. Cosine x to the fourth minus sine x to the fourth equals cosine of 2x. Oftentimes we want to start with the side that has a different input. See, on this side we have the 2x going into a cosine. However, the left-hand side is pretty tricky, so we will go ahead and try and work with that side today. Cosine to the fourth x minus sine to the fourth x is actually a difference of squares. Remember, an a squared minus a b squared can be written as a plus b times a minus b. Therefore, we will get two factors. But what would we need to have multiply to get cosine x to the fourth? It's actually going to be cosine squared x times another cosine squared x. Similarly, we'll have in the back, we'll have sine squared x and another sine squared x. And we need 1 plus 1 minus. Therefore, we get cosine squared x plus sine squared x times the quantity cosine squared x minus sine squared x. Something should look familiar. We have ourselves a cosine squared x plus sine squared x. We have an identity that says sine squared x plus cosine squared x always will equal 1. Therefore, we get just 1 times cosine squared x minus sine squared x, or cosine squared x minus sine squared x, since we're just multiplying by 1. Now this might look familiar. Let's go ahead and peek over at our double angle identities. Ding, 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 ding. Notice we have cosine squared a minus sine squared a is the cosine of 2a. So therefore, we can say this equals cosine of 2x, which is our right-hand side. Example 4, simplify each expression. A, 2 cosine squared of 5x minus 1. So I would pause here to see which, if any, of the formulas are you thinking of when you see that expression. I'm going to write the identity above so I can see the matching. I'm noticing that 2 cosine squared a minus 1 seems to be the pattern that they are getting at there. And that is equal to cosine of 2a. So what that tells me is that this expression can be written as the cosine of 2 times something. But I have to figure out what that something is. So looking at, that's why I like to line them up carefully so the 2's match, the cosine squareds match, and now we can see that a is 5x. So now, because it's equal to the cosine of 2a, I can plug in my a as 5x, or this is the same as cosine of 10x. Now these examples are a little contrived where they are really going to appear very similar to the identities. B, sine of 165 times cosine of 165. Looking at my identities, it's not quite as clear, but I do notice the only double angle identity that has a sine times a cosine is the sine of 2a. But this is going to require a little more work. Off to the side, I will write that identity out. Notice my original expression only has the sine and the cosine, but there's not this 2 in front of it. So one thing I could do is divide both sides by 2. Remember, these 2's can't cancel because sine of 2a is almost like its own variable. So now I have sine a times cosine a is the same as sine of 2a divided by 2. So now I'll go back over here and rewrite those to see what's lining up. So sine a cosine a is equal to sine of 2a all over 2. Therefore, this sine of 165 cosine 165 is going to be equivalent to the sine of 2 times some quantity all over 2. The 2 will multiply by a. So now I have to figure out what a is, and that's why I like to write them so close together, because now I can see that my a has to be 165 degrees. So now I can go ahead and multiply 2 times 165 degrees, and I end up getting 330 degrees. So this equals sine of 330 degrees all over 2. However, 330 degrees is a special angle. It's in quadrant 4 with reference angle 30 degrees. So my sine value is -1/2. Let's flip the denominator and multiply. So we get -1/2 times 1/2, or -1/4. And you could actually, just to check this, you could actually put sine of 165 times cosine of 165 into your calculator. Make sure you're in degree mode, and you will get -1/4 or -0.25. I hope you enjoyed this video. See you next time.